Next we have exercise 12. In this one we have to verify the following formula. Summation of lambda of n times the greatest integer value of capital N divided by small n, where in the sum small n varies from 1 to capital N, and this is equal to the greatest integer value of square root of capital N, and we have to prove that this holds for any positive integer capital N. We start the solution by applying theorem 611. You go and see the statement of the theorem, you will understand how. By this theorem, the left hand side equals this double summation. The outer sum of course is the one that we have here, and along with that the inner sum is the summation of lambda of t as d varies over all the positive divisors of n. In this theorem, you will see a function capital F. In this case, that capital F is this much, this inner sum. Now by exercise 7 part B from section 6.2, we find this, that this inner sum, that is summation of lambda of d as d varies over the positive divisors of n, equals this. If n is a perfect square, if n is the square of some integer n, then this sum is 1, otherwise it's 0. So what does that mean? It means that here sometimes it is 1 and sometimes it is 0, and because this is the general term in a sum, so we just need to now see how many ones we will get, and that number is this, the greatest integer value of square root of n. That is because this is also the number of perfect squares not exceeding capital N. The number of numbers of this type which are perfect squares and also which are less than or equal to capital N is this. That is why in this sum you will get that many terms like this which are equal to 1. The rest are 0. We do not have to worry about zeros. So this sum becomes equal to this. So that's how you have the proof. But still, this part may not really be very clear at once. So let's try to understand this part separately. The solution is over, but why this? Exactly how? Let's discuss like this. Let m be a positive integer such that m squared is less than or equal to capital N. Then obviously m is less than or equal to square root of n. You can take square root on both sides, and because everything involved here is positive, you don't have any problem. And this inequality implies this. How? See, this is by definition the greatest integer less than or equal to root n. M is some integer less than or equal to root n. This is the greatest of such integers. So m should be less than or equal to this greatest integer. That's how. Conversely, let k be a positive integer such that k satisfies this inequality. Okay, so we are going in the opposite direction now. Then you can take squares on both sides, obtaining this inequality. This square, however, is less than or equal to the square of root n. Where is this coming from? It comes from the fact that the greatest integer value of root n is itself less than or equal to root n. And both are positive. So there you can take squares on both sides, obtaining this inequality. This square, however, is n. So you see that you get back to that state, that if this is true, then k square needs to be less than or equal to capital N. So the square of a positive integer m is less than or equal to n. That means this happens if and only if m itself is less than or equal to the greatest integer value of root n. That means the type of numbers m square, okay, which will be less than or equal to root n is such that m should be less than or equal to this value. So what is the number of such m squares? Obviously the same as the number of this type of m, Now, how many positive integers satisfy this, that they are less than or equal to this integer? That number obviously is equal to this, because that many positive integers that they are starting from 1 and ending at this. That's why that number is this. So this very short video ends here. Actually, this was the last one in this section. Not really the last one, there is a number 13 also, but that's left to you because it's an odd numbered one. In the next section, we are going to see some applications of these ideas to dates and days in a calendar.